So, hello and welcome to the second Distinguished Carl Sagan Lecture. It's my pleasure to have you all here tonight. All the way from California to bring you the newest on the search for planets outside of our solar system. So, I'll just take a couple of minutes to introduce the Carl Sagan Institute here at Cornell. My name is Lisa Kaltenegger. I'm the director of the Carl Sagan Institute here at Cornell. And as it states there, we're developing the forensic toolkit to find life in the universe. What that means is life within the solar system, think for example Mars, and outside. And we have an astonishing, talented designer who put a small video together for all of you to see what the Carl Sagan Institute is all about. That hopefully will run now. And so the designer, Krista Downs, and the music was actually composed for this piece by Jesse Woolston. And so they are two space enthusiasts that love space as much as we do. And the idea is really what you saw, the three planets, that's kind of the image of the Carl Sagan Institute. The Earth, us, has the fingerprint, so of humankind. But the other two, if you look very careful, actually don't have any pattern, because we don't know if A, there's life on other planets yet, and if there is, why would we expect there to be humans in the first place? So we left it open in our logo, as well as, of course, in our search. And just a quick point of who is the Carl Sagan Institute here at Cornell. This is 36 faculty, and we have researchers and students, some of them are here, who encompass the Carl Sagan Institute here at Cornell. We're spanning 4 colleges and 14 departments and are ever growing by people who are fascinated by the search for life in the universe. So it spans from, of course, astronomy, that's my home department, all the way to music and the galaxy, all the way to engineering, biology, what could life be like, geophysics, and you see a couple of people in the audience laughing. They just saw which pictures I used for them. So, you know, the laughing people are probably team members that I have put up here. So it's an incredibly fun and interdisciplinary endeavor, the Carl Sagan Institute here at Cornell. And if you're interested, please just let me know. We're always looking for people who have great ideas or want to be part of an interesting discussion. And we also have a webpage, and in case you have not watched it yet, so on the 9th of November this year, for example, we released Carl Sagan's Lost Lecture. So last year we had a 40 years of Voyager event, and in that, Andrew, the widow of Carl Sagan and the amazing producer of, for example, Cosmos, the television series, and a writer, Emmy Peabody Award winner, she said on stage that the talk by Carl Sagan for his 60th birthday in Bailey Hall, just across the street, was one of the best talks he's ever given. And lo and behold, there was somebody in the audience who was like, wait a second, didn't I find a cassette that said Carl Sagan's 60th birthday lecture a couple of years ago? This is how we unearthed Carl Sagan's 60th birthday lecture, and luckily, people at the broadcast Cornell department could actually put it in a format that we could read. And so for all of you, it's online, and I think we released it for Carl Sagan's birthday. So in addition to about the research that we're doing in the Carl Sagan Institute, we're also doing things like communicating science to the public, and the lost lecture of Carl Sagan is really worth watching. Even now, it is beautiful, inspiring, and if you haven't watched it yet, you should. There were about 50,000 people who watched it the first weekend we released it, so it's definitely one to watch. It has a lot of interesting wisdom. And so, unfortunately, Andrew, the amazing lead on the creative Voyager message, as well as an Emmy and Peabody Award winner, as I said before, couldn't be here today. She usually is, but they're filming Cosmos, the TV series 2, and it's called Possible Worlds. So she's basically taking some of the research that we're doing here at the Carl Sagan Institute and putting her unique, beautiful vision of creativity to actually make it come alive in pictures in Cosmos Possible Worlds that you can see, I think, early next year. But she sent me a message, and I had asked her to tell me what the Carl Sagan Institute actually means to her as part of Carl Sagan's legacy. And if you allow me, I'll read it to you. So she sent me this email back that said, when Carl Sagan began his career in science, the search for life on other worlds was not considered a reputable astronomical pursuit. Carl and a handful of other scientists braved the scorn of many of their colleagues to break that taboo. He was the most fully alive human being I have ever known, and he yearned to find life elsewhere. It's a tribute to his character that he never trimmed his standards of evidence in order to believe that his deepest question had been answered. And she goes on and she says, how I wish I could tell him that the institute that bears his name is a vibrant collective of scientists who continue the searching that he and others began. The Carl Sagan Institute is innovating new strategies in this quest. I'm certain that he would have been proud and humbled that they do so in his name. And so, with that in mind too, this distinguished Carl Sagan lecture series that is part of what the Carl Sagan Institute does brings outstanding scientists as well as public communicators to Cornell here for you to interact and ask questions with. The first distinguished Carl Sagan lecturer was Lord Martin Lewis last year, who talked about surviving the century. And this night's distinguished Carl Sagan lecturer of 2018 is the amazing Natalie Batalha. She professionally was the Kepler scientist at NASA Ames, so she'll talk about the mission that sparked the discovery of thousands of worlds and is right now a professor at UC Santa Cruz. And among her many awards, there are three I wanted to highlight. So in 2017, she was elected as one of the Time magazine's most influential people, and Smithsonian Magazine gave her an Ingenuity Award. And she also holds the NASA Public Service Medal for her vision in communicating Kepler science to the public and for her outstanding leadership in coordinating the Kepler science teams. And this is the reason why we picked her as our second distinguished Carl Sagan lecturer. You were in for a treat, and I have to say we had Natalie here for the inauguration of the Carl Sagan Institute that you can also watch online on Cornellcast, but she only gave a very short talk then. And this is a picture of Natalie, Andrew, and me at that inauguration. And as you see, searching for life in the universe is an adventure and a lot of fun. And with that, I would like to introduce Natalie and bring her to the stage for an amazing lecture tonight. Thank you.
While I switch over, how is the sound? Is it okay? Seems reasonable. As you make your way to Ithaca, ask that the way be long. That's how it felt this morning at 6 a.m. when I got on a Greyhound bus. But then you get here. And every time I arrive here in Ithaca, and especially here at Cornell, I just feel how special this place is. And what an honor to be giving this lecture in the name of Carl Sagan. For me, that's really an amazing dream. Carl is one of the reasons why I'm doing what I do. The title of my talk is Lava Worlds to Living Worlds: How a NASA Mission Sparked the Search for Life Beyond the Solar System. It's a science talk. But a friend of mine recently asked me if I write poetry, and I said, yes, I do. And I sent her a picture of the whiteboard in my office. And I said, these numbers, these equations are the stanzas of my poem to the universe. And that's how I feel about my science. Science brings meaning to my life, and I find it very beautiful, very aesthetic. And so I hope to, yes, give you some numbers, but I hope that you see the beauty in the discoveries and where they're taking us as well. The search for, or these lava worlds to living worlds, and what we have found recently in the last, let's say, 20 years, has catalyzed the search for evidence of life beyond Earth. Some of you in this audience are young enough that you may live to see the day when we find evidence of another living world. When I say living world, I'm really talking about a planet or a place where life has taken a global toehold, where life is globally proliferating over the surface of that planet, and as opposed to hiding in a niche someplace. But really, there are multiple pathways for finding evidence of life, and the obvious one is searching for life in the solar system. While we look at all of the planets, and especially through the Voyager program that gave us our first family portraits of the planets, and now we've even gone to Mars, we don't see any evidence of life, but maybe there is evidence of death in the form of fossils. Maybe life existed in the solar system once upon a time. Or maybe life today is hiding in little niches. The other pathway for the search of life we call SETI searches, where SETI stands for the Search for Extraterrestrial Intelligence. The idea being that we catch radiation or some kind of signals from the universe, and we identify signals that have so much information content that they are not likely to be arising from normal astrophysical phenomenon, but perhaps through intelligence is what the acronym says, but then of course you have to come up with a definition of intelligence. We'll come back to that in a little bit. But the third pathway is the one that I'm here to talk to you about today, and this third pathway was opened up about 20 years ago, in fact 1995, with the first detection of a planet orbiting another normal star like our sun. And that's the story that I want to share with you today. But to say just a couple more words about solar system exploration, here, for example, is an amazing image of the surface of Mars. So spectacular are these images that you can get lost in them, and you feel like you can hear the Earth crunching underneath your boot. It feels like you're actually standing there. So we've had these rovers go to the surface of Mars, and we see evidence of dry lake beds, of gullies and rivers, dry rivers. We see erosion, we see sedimentary deposits, we see minerals that are formed, minerals that precipitate out of water and form globules like hematite. And all of this is evidence of a watery past for Mars. And I want to just use this as an opportunity to talk about why do we talk about water so much? NASA's constantly looking for the water. Why? Well, in order to answer that question, we have to look at life on Earth, and we have to ask ourselves, are there any commonalities of life on Earth? And we can go to some really crazy places on planet Earth. We can go to very dry places, very wet places, cold, hot, saline, high acidity. We can go to places where there's no sunlight. And we do find life wherever we look. Every rock that we lift, we find life lurking. And yet, you know, even though some of these life forms might not require sunshine, they might not require oxygen, they all have different needs and they're based on they have different requirements, but the one thing that they have in common is that they're all carbon-based. And carbon is very special in the universe. Besides hydrogen and helium, the next most abundant element in the universe is carbon. Carbon has special configuration as an atom with the way the electrons are orbiting the nucleus. It can fit together with other atoms, just like Legos, to create very large, complex chains of molecules. And life really is all about complexity. It's about the rise of complexity in the universe and how complexity is used to encode genetic information, for example. So when we look out into the other interstellar medium, for example, we see complex chains of carbon forming. We see amino acids. We see them in the solar system. They're everywhere. So the building blocks of RNA and DNA are already out there astrophysically in the cosmos. So this is what leads us to believe that life is likely to build upon carbon. And what we also observe is that the solvent that's required for all of the interesting chemical reactions in biology, like metabolism and cell transport, for example, that solvent is liquid water, uniformly across the board for all life forms on Earth. So we're searching for the water, and Mars looks like it was a watery place. Right now there is water on the surface of Mars, but it's not in liquid form, it's frozen, and there could be niches where that water melts. And so life could exist on Mars buried in certain niches. We've had many rovers go up to actually dig around and look at the chemistry, look at the geology and the chemistry. InSight, a new lander, just landed, a couple weeks ago? And that's going to measure the seismology of the planet and understand the interior. Mars 2020 is going to be the first rover capable of detecting organics. We're very excited about this. And Mars 2020 is also going to be capable of storing vials of samples, about 36 vials of samples. And the idea is in the future, we will have a mission that will go there and retrieve them, do a sample return. But there are other places in the solar system where we might look for life. This is an image that was taken by the Cassini orbiter that was orbiting Saturn. And it did a flyby of one of the satellites of Saturn called Enceladus and produced this amazingly beautiful image of backscattered light from plumes emanating from the surface of Enceladus. And the idea is that Enceladus is being heated from within by tidal forces that are squeezing the planet regularly as it orbits the satellite as it orbits the large planet Saturn. And that internal heat is actually melting some of the ice, producing an interface between liquid water and the rocky interior that could be a very interesting place to search for life, for this biogeochemistry. So that's the solar system exploration. I want to say a little bit more about SETI. SETI was largely defunded by the government in the 1990s. Carl Sagan himself was a proponent of SETI, along with people like Frank Drake and Jill Tarter, who was depicted by Jodie Foster in the movie Contact. Very recently, last year, the House Science and Technology Committee told NASA to spend $10 million. They didn't call it SETI research, they called it for the search for technosignatures, thereby removing this complexity of intelligence. And I think also broadening our vision of what this might entail. Traditionally, SETI is the search for radio signatures because in the 1950s, as television was coming online, we were transmitting I Love Lucy out into the universe, and that's how we were largely communicating with one another, was through radio waves, and we thought perhaps that's how other intelligent species communicate as well. Since that time, we've actually moved our technology more towards optic fibers, and so we don't use as much radio transmissions anymore. But the idea is the same. The idea is that life harnesses energy to do work. And that work could be anything from your automobile to communications to your blender that makes your smoothie in the morning. That's what life does. We harness energy to do work. And I think that that's a nice definition of life, or at least a partial definition of life. And so the idea is that when you harness energy to do work, conservation of energy says that you're going to have heat that's generated in some form. So the idea is that whatever data NASA takes in the future, we search that data routinely for anomalies that could be indicative of some kind of manifestation of life harnessing energy to do work. And so this is something to look forward to in the future. But again, we're here to talk about planets orbiting other stars, which we call exoplanets because the prefix exo means outside of, or outside of the solar system. So here's an artist's rendering of that first planet that was discovered orbiting another sun-like star. The name was 51 Peg B. Pegasi is the constellation, Pegasus, that it was found in. And I want to say a little bit about how this planet was detected. You all know that planets orbit their stars, but do you also know that stars also orbit their planets? In fact, the two objects are orbiting about their common center of mass, as is depicted in this cartoon, one in a top-down view and the other in a side or edge-on view. So if you can imagine a large star connected by a rod to a tiny planet, and you had to take your finger and balance that system someplace, that would be the center of mass, and that's the point about which both of these masses orbit. So it's going to be very close to the star itself, right? So the star is going to orbit just slightly. It's going to, we say, wobble, and this is called, therefore, the wobble method. So when we find planets, most of the time we're actually not taking a telescope and pointing it in the sky and saying, aha, there's a planet, like a traditional astronomer, you might imagine in your imagination. But we're actually observing it, inferring its existence indirectly. We're observing something about the star itself that is weird, and then infers the existence of the planet. And in this case, it would be the wobble. And the idea is that we would collect the starlight and we would spread it out into a spectrum, a rainbow. Take that white light that's coming in and we spread it out into a rainbow. And here you see an actual spectrum or rainbow of a star. And this spectrum has been spread out so far that we have to actually chop it up and stack it. So you've got red at the top, orange, yellow, green, blue, all the way down to the bottom. And what you notice about this rainbow of light is that there are black dots where light is missing. And those are called absorption lines. And these arise because the light that's being created through fusion processes in the core of the star diffuses its way out of the star gradually, and just before it's liberated into space, it passes through a thin atmosphere. And that atmosphere will eat away certain colors of light. And every chemical eats away different colors of light, thereby imparting a chemical fingerprint on the light by way of these dots that you see, okay? So we're going to come back to that idea later. But the way that we detect the wobble, oops, let me go back to this and start this animation. We're going to zoom in on one of these absences of light here in the yellow. And the grid that you see underlaying it is a grid of detectors that are measuring brightness. And what we notice is that the absence of light is actually shifting to and fro. And that's due to the motion. This is the Doppler effect. So the wobble method is also the Doppler method. It's evidence of the star moving towards you and away from you. And for this planet that was first discovered, that velocity of wobble was comparable to a car driving down the freeway. Okay, it was a pretty large velocity, easy to detect. And you see here the light levels kind of going up and down. And that is already kind of a first hint of how we might change this pictorial representation of a spectrum into something graphical. And we'll come back to that. Okay, but through this method, we were able to measure the mass of the planet. Because of the velocity. It's directly related to the velocity. How much is the planet pulling on the star is related to its mass. So we look at the velocity of the wobble and we get the mass. And this planet was a planet like Jupiter, orbiting something like 20 times closer to its star than Mercury is to our own sun. So that's very different than what we have in our own solar system. Here's a depiction of our own solar system with the sizes of the planets to scale, but not necessarily their separations, but they are in order. And in our own solar system, we've got the tiny rocky things close to the sun, and we've got the ice and gas giants far away from the sun. And now here we've got a planet the size of Jupiter, much closer to the star than Mercury is to our own sun. And that was a huge surprise. And it's certainly not the kind of place we would look for life. But it whetted our appetite, right? That goal was just tantalizingly within reach. But we couldn't find a planet like Earth orbiting a star like our sun in an orbit like Earth's using this wobble method, because Earth is tiny. Earth doesn't pull very hard on the star, especially from how far away it is. And the velocity it would cause of a wobble is more like the velocity of a ladybug crawling on the ground. It's very small. Our technology today is not quite there. So we needed a new technique. But before I share with you what that technique is, let's back up and let's go into fairy tale land. This is the fairy tale of Goldilocks. This is our Goldilocks. This is a tale from the 1800s by a British author. You don't necessarily need to know the fairy tale of Goldilocks, but basically the idea is that you've got this young, innocent girl who is going out into the dark unknown. She goes exploring, and she happens upon something that reminds her of home. She finds this in the middle of the forest. And then she goes into that home, and the rest of the story is about her trying to find her right place in that home. And she looks for things that are just right, things that she's familiar with. And so therein lies the idea of the just right world, or the Goldilocks world. When we talk about planets that are potentially habitable, we are thinking very simply in terms of what we can measure about a planet, which is actually not very much right now. The first thing we think about is temperature, because I already told you that water is really important. So we're looking for planets where water has the possibility, at least, it's not precluded from pooling on the surface of the planet, okay? So we don't want the planet to be too hot where water's all in vapor form. We don't want the planet to be too cold where water's all locked up in ice form. We want something in the just right place in the middle. And we run complicated models and we learn things. We learn really interesting things, like what happens when a planet is too hot. We learn about processes like runaway greenhouse, whereby water is evaporated and then stellar radiation breaks apart water molecules and hydrogen escapes, leaving only oxygen behind. So we learn about processes like that. And then we think about how to make a planet warm in the outer environs of a solar system. And we know that CO2, for example, is a great greenhouse gas. So we imagine, what if we pumped a lot of CO2 into a planetary atmosphere? Enough to make it really, really hot, like we see on Venus, right? Well, that works up until a certain point, and you've got so much CO2 in the atmosphere that it starts to condense out and create like a haze that starts to block the radiation, and then the process breaks down. So we learn about these processes because we're thinking, what are the limits of habitability? And when we think about the limits of habitability, that has very practical implications for life right here on planet Earth. How far can we push our own planet and maintain a sustainable biosphere? Okay, so orbit is very important, where the planet is orbiting. The other thing that we think is very important is size. We run models of how planets form. A planet like Earth is mostly magnesium, iron, silicates. Those kind of elements actually aren't very common in the universe. So there's a limit to the size of a rocky core that you can actually create, because just the basic building blocks aren't there in abundance. But there's tons of hydrogen and helium. And when a rocky core gets to be a certain size, the planet very efficiently starts to accrete onto it hydrogen and helium and the molecules that are formed from hydrogen, like water, hydrocarbon gases, etc., ammonia. And so here's a schematic of our ice and gas giants, Jupiter, Saturn, Uranus, and Neptune. And you notice in these cutaways that they all have a rocky core. And it's about the size of planet Earth, which is cartooned there in the upper right. But again, you've got these envelopes of hydrogen and helium. A lot of it is in gaseous form, some molecules, interesting molecules. And by time you burrow down to the rock, where you have the heavy elements that life is made out of, your cells are made out of, the pressures are just so high that complex molecular chains like DNA and RNA can't stay together, right? So size, we think, is also important. So what we're looking for are tiny planets, like our terrestrial planets, in orbits where liquid water could exist. And here is where the Kepler mission, NASA's Kepler mission, comes into play. NASA's Kepler mission was the first mission capable of detecting large numbers of potentially habitable Earth-sized planets. It's a space telescope. Here you see a picture of it on the left in the clean room at Ball Aerospace. The mirror, the light collecting bucket, is about 1 meter across. Very simple design, no moving parts except for some gyroscopes that maintain pointing. And all it's meant to do is measure the brightnesses of stars very precisely. Because it's going to use a methodology called the transit method for finding planets. The idea is you measure the brightnesses of stars so accurately that when a planet in its orbit about this star, when that orbital plane is aligned just right, its shadow will sweep across the face of your telescope, and your telescope will perceive its presence as a momentary dimming of light. And that dimming of light, like you see here illustrated in the green cartoon as a plot of brightness versus time, it repeats. So you see it come back around once an orbit. And so you measure the orbital, what we call the orbital period of the planet, the time interval between these dimmings of light. There was a scientist in the 1600s, his name was Johannes Kepler. He's our namesake. Johannes Kepler taught us that there is a correlation or a direct relation between the orbital period of a planet and the distance between the star and the planet. That's how we know if the planet is in that Goldilocks zone or not. We measure the orbital period, we get the separation, we get the distance. Okay. So to recap, Kepler measures two things. The amount of dimming of light tells us the size of the planet. Orbital period tells us the distance between the planet and the star. Here in this cartoon on the left, I've got a disk the size of Jupiter occulting its star. That's going to remove 1% of the light, 1 light bulb out of 100. On the right, you've got a disk that's the size of Earth, and you can barely see it. It looks like a speck of dust on the lens, right? It's tinier than a sunspot. And it removes 1 part per 10,000 of the light. So if you can imagine a very tall skyscraper, maybe 18 stories high, and it's night, and every window is illuminated, and one person goes to the window and lowers the blinds by about 1 centimeter, that's the change in brightness that you have to be able to measure to see the dimming of light of an Earth-like planet. It's very tiny. So it's a simple idea, but the engineering that's required to maintain that stability is what makes it so elegant. Here's an example of the data. So here are the numbers, that's the stanza of my poem to the universe. All the white points that you see are brightness measurements as a function of time over a period of about 300 days. So you notice a few things. First of all, like for example, around day 100, there's a gap where there's no data. The telescope shut off. It had an issue that had to be solved, and it shut off. Then you also notice that the white points are kind of jumbled, kind of up and down and jumbled, and that's measurement uncertainty. But then you notice that there are more points raining down than are raining up. And that's because there are transiting planets in this series of data that we call a light curve. It's how the light is changing. So can you see the first one readily? It's right there. See that? This planet orbits its star once every 4 days, and it's a little over twice the size of Earth. So now we'll zoom in on this dimming of light. Okay, let's zoom in on it, and it's marked in cyan blue, so there it is. Okay, but look at the brightness measurements next to it. Buried in there, you also see there are more points raining down than raining up, right? Because there is another planet transiting this star. Maybe you've pinned it down by now. There it is marked in red. And this planet is only 40% larger than the Earth, and it's orbiting its star once every 20 days. So this too is much closer to its star than Mercury is to our own sun. But this is the game that we're playing. Okay. So now in one scatter plot, I want to give you the sum total of what Kepler found over at least its first 4 years of operations. And so I'm just going to plot on the y-axis the radius that we measure, and on the x-axis the orbital period. Remember, those are the two things that we measure. So this is what the scene looked like on the eve of Kepler's launch. Every point you see in this diagram is a planet discovery. Some are blue, some are colored pink. The blue ones were planets that were discovered through the Swabble method. The pink ones were planets that were discovered by the transit method, but largely from ground-based telescopes. And on the eve of Kepler's launch, 85% of the planets known to humans were larger than Neptune, which you can discern from the graphic from the horizontal lines for reference that I put in, okay? So now I'm going to add the Kepler discoveries in yellow, and this is what it looks like. So the blinders were lifted that were obscuring the small population of planets in the galaxy. We couldn't see them before because we didn't have the sensitivity with our methodologies. Kepler put a new piece of technology up into space, and now those blinders were lifted. And we found a galaxy replete with small planets. Now, over 90% of the planets known to humans are smaller than Neptune. And there is a wealth of information in this one diagram that I don't have time to talk to you about today. But you'll notice, for example, that there are no planets in the bottom right-hand corner. That, again, is not because that they don't exist. It's because we've reached the sensitivity limit of even this new piece of technology. So the diagram will fill in as we gain new capability. But there are other gaps in this diagram which are real and are giving us a wealth of information about how planets form and evolve. But I want to give you a couple of takeaway messages from Kepler discoveries. And the first of those is that the diversity of planets in the galaxy far exceeds the diversity of planets in our own solar system. We found crazy, weird places that we didn't know exist. Some of them were already depicted in science fiction. Some of them were new. And here what you're seeing are thumbnails of artist renderings to try and help us imagine what these worlds are like, based part on imagination, but also grounded in the numbers, the facts of what we know about these planets. And so I'll just run through a few of them to give you a flavor for the diversity of planets out there. In the upper left-hand corner, this artist rendering is supposed to depict a planet orbiting a dead star, a white dwarf or a pulsar or a neutron star. But it also, to me, represents the fact that we have found planets the age of the galaxy itself, which is almost 13 billion years old. This fact amazes me for a couple of reasons. First, we didn't think that planets could form that early on because elements like iron and magnesium and silicates are produced in the cores of stars that go supernova and enrich subsequent generations of stars. Now we're finding that that process happens very quickly. Right out the gate, you've got type 2 supernovae that enrich the environment sufficiently for planet formation, for rocky cores. But the second reason why this fact amazes me is I'm thinking, what would life do given 13 billion years to evolve? We have only been on this planet for a very short time, intelligent life, or eukaryotes, let's say. The whole tree of life that led to us has only been on this planet for, let's say, 2 billion years, not very long. Imagine if there is a species or a planet that was able to harbor life for almost 13 billion years. What is possible in that time frame? Okay, the next cartoon represents lava worlds. That's one of the title of my talk. The lava worlds were a class of planet that was one of the first, they were the first rocky planets that the Kepler mission found. These are rocky worlds, and we know that because we can measure their densities, their average densities. They are orbiting so close to their parent star that the star-facing side has temperatures in excess of that required to melt not just rock, but iron at standard temperature and pressure. So you have an ocean that's bigger than the Pacific Ocean, but it's not made of water, it's made of molten rock. And there's a whole class of these planets that have been discovered. If you take that even to more of an extreme and you move the planet even closer to its star, the planet will photodisintegrate before our eyes. And we see that in the form of these cometary-like tails that are very large, very extended, optically thick and opaque. And what that does is when this object transits its star, it crosses the stellar disk and you get that nice dimming of light. But then as it goes by, the tail starts to block more and more light and it gets deeper. And then it takes a very long time for the light level to come back up to normal. So it has a completely different shape than a normal transit of a planet. And that's what is an indication of these photodisintegrating planets. Down at the bottom, we have these blue worlds that are supposed to represent ocean worlds. These are planets that are not ice and gas giants necessarily, but they are also not rocky worlds in that their densities are slightly lower, indicative of the fact that they've got some amount of what we call volatiles in their envelope, things like water. And we imagine that there are likely planets that are entirely enveloped in an ocean, in a thick ocean. Imagine, for example, you took a planet like Neptune, made it a little smaller, and then you drug it in and plunked it down at Earth's orbit where it receives much more energy. What would happen to that planet is the question. Okay, then we've got planets that are orbiting not one but two stars. This was depicted in Star Wars. Luke Skywalker's homeworld Tatooine had two stars. So you go out in the morning and you look at sunrise in the east and you would see not one but two stars rising, orbiting one another, doing a pas de deux across the sky. Those are the circumbinaries. And then lastly, we have planets orbiting in strange environments, orbiting stars in gravitationally bound clusters of stars. If you happen to live on a world like this, you would look up and you would see a bejeweled sky because the density of stars in that environment is very high. So lots of really interesting places to spark the imagination. Kepler has also found numerous multiple planet systems, and here's a beautiful video showing all of these worlds. I think let's see, we don't seem to have volume. Is that my computer? There we go. Got a soundtrack going on here. What I love about this, so you've already seen an example of one where there were two sets of periodic transit sequences. We have stars with 2, 3, 4, 5, even up to 8 planets known to be orbiting them. What I love about this diagram is that it spans the lifetime of Kepler and it uses the orbital periods of the actual planets that we discovered and the times of their transits. So what you're seeing here is actually what's happening in the galaxy, just sped up. So it's 4 years of data sped up into these couple of minutes. But it shows all of the relative positions of all of these planets during that time and really drives home the point that the universe is this amazingly dynamic place. Okay, one more graph that I'm going to show you. I took that scatter plot that I showed you and I've just made a bar graph out of it. I'm just counting, okay? So on the x-axis, I have a bunch of ranges of sizes. So the first one, for example, is 0.5 the times the radius of Earth to 0.7. That'd be like the Mars-sized planets. And et cetera, going up to Jupiter. So you can ignore those numbers because I colored the bars for you. So the brown bars are supposed to indicate terrestrial-sized planets, from Mars up to maybe a super Earth. The blue bars, on the other hand, represent the gas and ice giants like Jupiter, Saturn, Uranus, and Neptune. And you can see the planet sizes represented on top. And what's remarkable about this simple counting bar graph is that the most common planet known to humanity right now is literally this gray area in between. We have no example of this in our own solar system, and yet they're everywhere. There are a lot of these things, and so we call them super-Earths or maybe sub-Neptunes, we're not really sure. But this is where that ocean world I told you about fits in, and it's going to be very exciting to understand what this new class of planets is like. Okay, Kepler is a demographics mission. I mean, we had planets in retail before, one at a time, kind of like stamp collecting. But now Kepler is doing planets in wholesale, right? Now we've got thousands of planets. And when you have thousands of planets, you can actually start to do demographic surveys. You can start to understand the demographics of planets in the galaxy, right? So we want to do that. We want to take this bar graph and we want to correct it to say something meaningful about the intrinsic population of planets in the galaxy. So it's really analogous to calling up 1,000 people and asking them what cereal they eat for breakfast. Imagine you did that, but you called during the day when all the kids are home. Nobody's going to say that they eat Fruit Loops, right? Or what is the most sugary cereal out these days? I don't know. So if you called during a time when kids were at home, you would get a completely different answer, right? So you're going to need to somehow calibrate your results and correct for that bias. And when we observe for planets, when we look for planets, we have biases like that as well. So we're going to, and also one of these biases you already know, by the way. This method of finding planets requires that you have just the right geometry, right? But the orbital planes of planets are related to the spin of stars, and the spin of stars in the galaxy are all randomly oriented. So the probability of actually having one align just right so that that shadow sweeps across the face of your telescope, that probability is like 0.5%, maybe 10% at most. That means for every one planet you found, there are 10 to even 200 others that you didn't find. So if you really want to know the true population of planets in the galaxy, that's another correction factor you're going to have to make. Okay, so now I'm going to show you another histogram. I'm not going to show you the Mars, the tiny planets, because there are so few of them. I have very large error bars. But the rest of them I'm going to show you after making that correction. And what you see is that when I correct for the biases, now on my y-axis, I'm measuring the average number of planets per star. And the brown bar grew, and the blue bars were suppressed. So this diagram tells me that at least for orbits like Earth's and inward, small planets rule the land. Small planets are orders of magnitude more abundant in these orbits around other stars. But there's another interesting factoid that emerges from this histogram. If you add up the numbers associated with each of these bars, for example, the brown bar is up at 0.4, then we've got bars around 0.3, 0.3, etc., and you add up those numbers, you quickly get to a number greater than 1. So what this tells me is that the average number of planets per star is at least 1. At least. Remember, I threw away all the Mars and Mercuries. I haven't even probed beyond an Earth orbit. I haven't even probed the realm of the ice and gas giants. So I'm saying at least 1. And so that really changes the way that we see the starry sky. When you look up into the sky, the pinpoints of light that you see are not just stars. They are planetary systems. Planets are everywhere. That's the takeaway message. Okay, but what about our Goldilocks planets? How can I share with you the abundance of Goldilocks planets in the galaxy? Well, let's take the galaxy itself and let's shrink it to the size of the continental United States. And there we are over in lovely Ithaca, and we turn west. We put our back to the Atlantic, we turn west, and we look over the continental United States, and we ask ourselves the question, where is the nearest potentially habitable planet likely to be, based on these statistics, based on what we found? What do you think the answer is going to be? It turns out that the nearest potentially habitable planet, looking out over the continent, is like here at the football stadium. In galactic terms, that's within 10 light years at 95% confidence level. That's very close. It's a stone's throw away. This is why I say that NASA's Kepler mission has catalyzed the search for life beyond the solar system, because it's just a stone's throw away. We know how to build the technology to do this. We just need the resources and the green light to do it. So, to recap, the Kepler mission was this space-based mission. It stared for 4 years at one constellation, one patch of sky in the constellation of Cygnus and Lyra, right under the wing of Cygnus the Swan. And it took a brightness measurement of about 170,000 stars simultaneously once every 30 minutes for 4 years unblinkingly in order to find these dimmings of light, these little ephemeral dimmings of light. After that 4 years, NASA actually gave us the green light to keep observing. And if we'd had our druthers, we would have kept observing Cygnus for another until the spacecraft ran out of fuel. But we lost a gyroscope. It kind of ground up to a halt and stopped spinning. And those gyroscopes are used to control the roll and the motion of the telescope and keep the pointing very stable. So now, without one gyroscope, one axis of rotation was open loop. We couldn't control it, so the spacecraft would just be spinning. We couldn't point stably at that region of sky. Luckily, there's a very interesting feature of our telescope, and that is that the solar panels are perfectly symmetric about one axis. So if we turned those solar panels directly at the sun, it would be kind of like pointing a rowboat directly upstream. So even though you've got this thing flowing towards you, if your boat is perfectly symmetric, you can hold that angle steadily. And so that's what the Kepler spacecraft did. It oriented itself so that the panels were perfectly symmetric with the solar radiation and held that one axis along that direction. And in doing so, it was able to observe different fields, because now you can point in the other angles along what's called the ecliptic. And so you see these funny geometric patches that represent the Kepler detectors projected onto the sky. It's about the size of my open hand on the sky. And the ecliptic is the zodiac. It's where the zodiacal constellations are. It marks the plane of our solar system planets projected onto the sky. And so Kepler did this for a whole another 4 years and doubled the lifetime of the mission, which was really exciting and opened up a lot of new astrophysics. But we knew that all good things must come to an end, because Kepler had a finite amount of fuel on board. The fuel is used to desaturate or spin down the gyroscopes. Every once in a while they have to be spun down, because with time they just start spinning faster and faster. And so there were 3 gallons of hydrazine fuel on board the spacecraft that fire thrusters, tiny thrusters, to spin down the gyroscopes. And we knew, the engineers told us, look, the fuel's likely to run out like sometime around the end of 2018. And we don't have a fuel gauge on board the spacecraft, but we do measure the pressure inside the fuel tank. And sure enough, around October, beginning of November, there was a signal that the spacecraft was running out of fuel. And so we saw headlines like this: R.I.P. Kepler. Kepler, the little NASA spacecraft that could, no longer can. So long, Kepler, and thanks for all the planets. It was very dramatic and depressing. Now, the reporters always asked me, so are you sad now that Kepler is done? And honestly, I had not a single drop of sadness in me because we accomplished everything we set out to do and more. So I felt like we really got everything we possibly could and more out of that spacecraft. But one little historical tidbit, after seeing that the pressure in the fuel tank was so low and that the spacecraft had to be powered down, the engineers got to work to start executing that sequence. Everything has to be powered down in a very safe way. We don't allow a spacecraft with systems running to just go off on its merry way forever and ever. So we shut everything down safely. And the Ball engineers did that on local time, November 15th, which just so happened to be, you can't make this stuff up, the anniversary of the death of Johannes Kepler himself. There is a little thing about UT, Universal Time, versus local time. So yeah, okay, Kepler was actually on UT the 16th, but it was still quite remarkable that the spacecraft was shut down on the anniversary of the passing of Johannes Kepler. It was very lovely. And so, of course, I had to share the epitaph that Kepler wrote for his own tombstone. I used to measure the heavens, now I measure the shadows of earth. And of course, Kepler, the spacecraft's epitaph, had to read, I used to measure the shadows of Earth's, because that's exactly what it did. And who says that engineers are not poets? The Ball engineers labeled this command sequence the Goodnight command, the Goodnight Sequence. Here is an actual snapshot that our instrument scientist furiously took with his phone, you know, trying to press those two buttons to take a snapshot of what he's seeing. This is the operations blog of the spacecraft. And so you've got the engineers writing things like, for example, Mom has given the go to send the good night command. Mom does not actually stand for Mom, it's the mission operations manager, but gave the go. Good night sequence command start. FD, that's the flight director, is calling it. We believe the good night sequence has made it in. And finally, so long, Kepler, and thanks for all the fish. But this good night sequence actually was inspired by the movie Interstellar. There's a famous scene. Interstellar, the movie, actually made the poem, the Dylan Thomas poem, quite famous. And so I went ahead and pirated that scene off of YouTube for your viewing pleasure. Very, very, very lovely and fitting end to the Kepler spacecraft, and rage it did. This is Kepler by the numbers, 9.6 years in space. It traveled 94 million miles in that time, orbiting the sun. And on just 3 gallons of fuel, it observed 530,000 stars, discovered 2,662 confirmed planets with another 2,000 waiting to be confirmed, discovered 61 supernovae, published almost 3,000 scientific papers, and uploaded only 678 gigabytes of data for all that science. So, pretty good run. I'd like to give you at least a flavor for the future, because you studied so hard the stellar spectra, so I want to come back to that briefly. The next era, we had this era of demographics. The next era is going to be an era of atmospheric characterization. These transiting planets are very special, because as they transit their star, some of the starlight is going to filter through the atmosphere of the planet before it reaches our telescopes. And if it does that, that atmosphere is going to impart its own chemical fingerprint on the light. And if we can disentangle the stellar light from that light that goes through the atmosphere, we can actually see that chemical fingerprint. And this is what's going to be done in the near-term future with instruments like the Webb Space Telescope, which is currently under construction and is the successor to the Hubble Space Telescope. That's going to be done from space. It'll be launched in 2021. And from the ground, most likely, with the next generation of telescopes. The next largest telescopes in the world are going to be approximately 30 meters in diameter. This is the 30-meter telescope. It's comprised of 492 hexagonal segments. It's due for completion in 2027. We got the legal go-ahead to build it on top of a mountain in Hawaii. There's another one like it being built in the southern hemisphere in Chile, so we'll have two eyes to the universe, one in the north, one in the south. So with these instruments, we'll be able to do this, but it's not quite as easy as that cartoon made it seem. That was a fake planet, exaggerated to give you the feel of how this light filters through the atmosphere. This is an actual, in fact, this is the only actual, whoops, what happened? I don't know why I did that. This is the only actual planet picture image that I've shown, I think, tonight, besides Mars, the surface of Mars. This is Venus transiting the sun. This is an actual image, not an artist's rendering. Can you see Venus, the Venusian atmosphere? It's very hard to see. I can only see it if I look projected against the blackness of space. Then I can see a very, very thin yellow trace. That is the Venusian atmosphere. It only has a scale height of something like 5 kilometers. It's very tiny. So the chemical fingerprint that's going towards your telescope is buried in the glare of this light, and it's going to be very tiny and very difficult to see. In order to play this game with planets that are probably larger than Venus, what we need is to find all of the planets that are closest to the solar system, so that we have the best fighting chance of beating down the noise to see these very tiny signals. And that's being done by a mission called TESS, which is the Transiting Exoplanet Survey Satellite. It has 4 cameras inside of it, all angled slightly differently so that it observes a longitude strip. It's going to point at one longitude strip, stare at it for about 30 days, and then clock over and stare at another longitude strip. And in that fashion is going to encircle the northern or the southern hemisphere first, and then the second year it flips and it does the northern hemisphere. And so in this way, it will actually cover almost the entire sky to find all of these nearby planetary systems. So in the beginning, I showed you a pictorial representation of a rainbow from a star, a spectrum. But you got the idea that at every single color, we could measure the brightness. And when there is missing light, our brightness measurement would take a dive and then come back up and then take another dive, and you'd have wiggles up and down depending on what chemicals, atoms, gas and gas form, or molecules are present in the atmosphere. And for planets, there are probably lots of molecules, like in our own atmosphere, molecules using nitrogen, water, methane, carbon dioxide, etc. And so here, this lovely artist rendering, well, actually, these are images of solar system planets. I shouldn't say that they're artist renderings. These are actual images of solar system planets. This is work that's been done right here within the Carl Sagan Institute here at Cornell. These are what those wiggles of brightness with all of its ups and downs due to the chemical fingerprint. So basically a graphical representation of the spectrum. This is what they look like for solar system objects. And you can see that they are very diverse. Depending on the world, you get completely different wiggles. So the wiggles are going to tell us a lot about whether planets have greenhouse gases, for example. And in the future, with future telescopes, we'll even be able to look for metabolic byproducts of life on a living world which has taken a global toehold of its planet and created a global biosphere, putting things like oxygen gas into the atmosphere through photosynthesis, for example, or methane. This is the idea of how we're going to find evidence of a living world. It will likely be by looking for the chemical fingerprint of its surfaces and its atmosphere. So that's what we have to look forward to in the future. The James Webb Space Telescope is going to do this in spades for larger planets. If we want to really be able to search for life, we're going to have to do that with a future piece of technology, and that technology is being planned today. And instead of relying on observations of transiting planets where light is filtering through that little yellow line that was Venus's atmosphere, we want to find a way to collect light bouncing off the entire surface of the planet, reflected light. Because that light, now we've got more photons available, it still has to pass through the atmosphere on its way back, and you catch it, spread it out into a spectrum, you could do the same thing. But it's very hard to see the reflected light off of a planet because planets are like mosquitoes flying around a spotlight, a searchlight. They're literally lost in the glare of their parent stars. And in order to see the planet, like we're seeing the firefly here, we are going to have to build a telescope that can put a giant thumb in the sky to block the starlight to see what's nearby. And there are a couple ways we can do that. We can put our thumb inside the telescope as a tiny disc, or we can put a literally giant thumb in the sky flying as a separate spacecraft. We call this a star shade. A lot of credits in the front, but this animation is going to show you what I mean by a star shade. It's an object with a very specific shape. It launches together with a telescope or independently. The telescope here is detaching from the star shade, and again, the star shade is going to be this giant thumb in the sky. It's shaped more or less like a sunflower because of the way that it's controlling the diffraction of light. And then the spacecraft, or that star shade, has its own control system. It's going to fly far away so that it's exactly the size of the star that it's trying to cover up, and thereby reveals the tiny, faint spots of light that are the planets. So in this way, we hope in the future, let's say within the next 30 years, we hope to have a piece of technology. I'm going to pause it, actually. They're building this at JPL. Right now, they're doing technology demonstrations to build these star shades. So that is work in process. But I want to save some time for questions, so I'm going to go to one of my last slides. This is happening right now. In the next 30 years, we think we'll have the resources to actually test this in space, to do this kind of mission. That's why in the beginning, I said that some of you in this audience are probably young enough that you will see the day that we find evidence of a living world beyond the solar system. This is written into NASA's 30-year roadmap. Is there life on other worlds? For the first time in human history, we have finally been able to embark on the systematic scientific pursuit of an answer. So finally, I want to return to our Goldilocks. This is our heroine. She's returning, but now in a different context. In the actual fairy tale of Goldilocks, she goes into the house uninvited. She uses up their resources, and then she finally encounters life and she runs away. So I think we need to rewrite the narrative a little bit. People often ask me, why are we searching for these planets? And it's not to find Earth 2.0. It's not that we want to find a backup plan for Earth, for when we destroy our own planet. To the contrary, I think we do this one, for the sake of knowledge itself, but also to understand the limits of planetary habitability, because it has a direct impact on figuring out how to have a sustainable future for the human species right here on Earth. It allows us to contemplate deep time, both in the past and in the future, and on geological timescales, but also on cosmic timescales. And I think we do this because humans have the innate desire to connect with whatever awareness and complexity that exists out there in the galaxy. So I think that in doing so, we raise awareness here on planet Earth, and I think that ultimately we increase the empathy of all human beings here on planet Earth. And for me, that's why we are searching for life. So I will end there, and thank you so much for coming out and joining us and allow me to share this story with you. Do we have time for questions?
Yes, of course. So we'll have 2 microphones, so please line up behind. If you have a question, Natalie will answer it. We are live streaming this on several platforms too, so please go and speak into the mic or nobody else is going to hear what you have to say. So if you have any questions, please just walk up to the mic and then ask about life, the universe, or all the fish.
You could just raise your hand too, but I don't know if I'll hear you. Anybody have a question?
Sorry for the walk.
Maybe we could have a runner, because the microphone comes off the stand there. That might be faster. Okay.
I had thought that I would wait until all the scientists had their go at the scientific questions they had before
This talk is not for them, it's for you.
The question I have is, you are obviously a very successful scientist. And I think we all know that women in science, and especially in physics and math, have been widely discriminated against. And for the sake of the young women scientists in this audience, I wonder if you have advice for them. I am past that stage, obviously, but I try to help young women conquer what is obviously still a very strong bias against women in science.
The statistics would agree with you. So my own daughter has a PhD in astrophysics. So you would think I would know a lot about this. But when I did any kind of activity in science, it was an internship when I was an undergrad. So I got this thing called a research experience for undergrads at the Wyoming Infrared Observatory, and I arrived there, and they took a picture of the intern group, the cohort that summer. And there's this great picture. It's me in this bright magenta pink sweater, surrounded by men. Then fast forward like 25 years, my daughter sends me a picture of her freshman class at graduate school. She had just started her PhD in astrophysics. And she sends me this picture of her freshman class, and it's her in the middle wearing a bright pink blouse surrounded by men. And I thought to myself, my goodness, 25 years has gone by and nothing has changed. Why does it take so long? So, do I have advice? I would say that there are many opportunities. I would say that organizations are making very aggressive attempts to correct the status quo. What happens, though, is when you are trying to do something difficult, that's really challenging and really hard, all human beings, whenever they try to do something difficult, they experience self-doubt. That's normal, right? But when you look around at the room and you are different than every other person in that room, your self-doubt becomes like this, like there's evidence that it exists because you're different. And this is well documented. It's called the imposter syndrome. And it's particularly strong when you are an underrepresented group. So awareness of that is really 90% of the battle, right? Just to be aware of it and to just always look at other evidence for how you are successful and remind yourself and not be afraid to take risks. And the best thing, I think, the most helpful thing I can do for those in the audience, the young people in the audience, is to share with you the fact that I started college as a business major. I wasn't planning on doing science. I didn't think it was consistent with what I felt my strengths and weaknesses were. I had this weird perception of what a scientist is. I thought it was a white man who wore a lab coat and sat in a room and poured chemicals into beakers all day. I didn't see that as something I wanted to do, or I didn't even feel that it aligned with what I thought I was good at. But in the backdrop of all of that, I had Carl Sagan to read. I wanted to do something in my life that gave meaning to my life. I had this aesthetic of beauty and philosophy, and the space shuttle program was going on in the backdrop. And at just a certain point in my educational path, after I took an economics class, of course, and I hated it, I said to myself, Natalie, get a grip. If you could do anything, what would it be? And the immediate answer that came to my mind was work for the space program. And so I enrolled in a physics class. And taking that physics class was horribly difficult. It was a new way of thinking I had never experienced before, and I was really bad at it at first. And I had to seek colleagues, I had to seek mentors in order to just get my momentum, just to get me started. You know, all these vectors and forces and resolving them, I did not know how to do that. But that tiny little push was all the encouragement I needed. And what ended up happening was, even though I was bad at it at first, I was blown away by the beauty of being able to write down an equation to explain a rainbow. That was absolutely incredible to me, that the universe was not this chaotic collection of facts, but rather something ordered, that all of a sudden I felt like all the mysteries of the universe could be revealed to me. And the power of that and the excitement was really overwhelming. So I think the only advice I can say is to be aware of the imposter syndrome and do what you love, even if you suck at it.
And then I think I'm gonna ask a cheeky science question.
Oh boy.
And a 5, and then in a 10-year horizon. What are you the most excited about in terms of search for life? Except the Carl Sagan Institute, of course.
On the 5-year time scale, I'm very excited to understand what the gray area in between is. That's something that the James Webb Space Telescope can really reveal to us. Right now, we know that it exists because we measure the bulk density, the radius and the mass of some of these planets. And so we know that these are kind of low density worlds. That's kind of a bottom-up approach. With Webb, we're going to do this top-down approach where we look at the atmosphere, see what the atmosphere is made out of, and we should be able to tie those two together. So I'm very curious about what those are. I'm also very curious to know there is growing evidence that even the planets that are Earth-sized have compositional diversity. And that means that there are probably planets out there that are entirely covered in an ocean, and the thickness of that ocean matters. If the ocean is too thick, then you've got too much of a good thing. And now you don't have interesting interfaces at reasonable pressures where the rock and the water interact. So I really would like to know what the compositional diversity of Earth-sized planets is, but I think that's more on the 10-year time scale, because that's going to require better instrumentation to measure the masses of small planets and better instruments to look at the atmospheres of the tiniest planets.
Hi. Obviously, you're an expert on Kepler, but just looking forward to TESS and any other missions that might be on the horizon, what might they teach us? What might they reveal that goes beyond what Kepler has done, you know, pending this 30-year sunshade kind of level of project?
Yeah. Well, I mean, that was really just exactly what I just said. I think that TESS's job is to find the nearby transiting planets. It's the transiting planets that are going to be observed with the Webb Space Telescope, not necessarily the Earth-sized planets, but the larger ones that fall in that gray area in between. So we're going to be able to sort out kind of what these Neptunes and super-Earths are with these missions. And TESS already launched. It's already collecting data. It's already announced its first planets. It has a couple hundred, I think, planet candidates that are being followed up by ground-based telescopes. So it's already well underway.
What are your thoughts on what's going on with Tabby's star?
Tabby's star. For those of you that don't know, going back to this idea of technosignatures and just always looking at all NASA data that's in the public archive for anomalies, because citizen scientists looking at Kepler data found an anomaly. One of the brightness measurements, or these light curves I was talking about, has periodic dimming, or dimmings of light, but they're not periodic. And they have weird shapes. And they are sometimes really deep and sometimes really shallow. And sometimes you get one and sometimes you get a swarm of little ones. And this was a huge mystery. We couldn't understand what was causing this. If a very deep transit implies something very large, and if there's something very large, you might expect to be able to see the wobble of the star due to that object. We didn't see it. So people were thinking for a long time about what this could be, and it hit the news because one astronomer, a couple of astronomers, posited that it could be a technosignature. Maybe this civilization is harnessing the energy of the entire star to do work. And to harness the energy of the entire star, you have to build superstructures. Maybe we're seeing these superstructures blocking out light from the star. So this was really exciting, and it was a great mystery because it was a puzzling system. But another hypothesis that was put forward is that you have a lot of circumstellar material. Perhaps there was a collision of a planet that broke up a bunch of debris, and now you're seeing all of this rubble, or maybe a disk, an extended disk, and maybe the disk is warped or precessing and blocking out large amounts of light. But then we looked in the infrared for any kind of heat signature of dust around the system, and at first we didn't see any. And so that was puzzling as well. But the most recent results on Tabby Star is that there is indeed a signature in the infrared of some kind of dust emission in the circumstellar environment. So it looks like Tabby Star is going to be explained by dust.
If we now have, from Kepler, evidence of a large number of Earth-size or roughly Earth-size rocky worlds, and yet after a couple of decades of SETI, we have no evidence of technology. Mm-hmm. What does that say? Might we be the only technological life in the galaxy?
It says absolutely nothing, because, sorry to be so blunt, because SETI searches today only have the sensitivity to see a signal that's being directly beamed at us, a hugely energetic signal that somebody is actually focusing right at us. Why would a civilization do that? Why would they expend the resources? Energy is so precious. Why would you do that? So it's hard for me to imagine that. I mean, maybe there's one civilization somewhere that's doing that. I don't know. But for many civilizations to be doing that, I don't buy it. Since 1950. So it's traveled 60 light years. That's nothing. That's nothing. Yeah, so I don't think it tells us much.
So Kepler mission seems based on the assumption of our understanding of the Earth. So is that possible that life exists being without any similarity to the Earth?
Absolutely. Yeah, we were talking about this at dinner. I get that question a lot. Of course, we don't want to be biased by this one example of life that we have. And life might manifest itself in various ways. I do think that nature, if you look at life on planet Earth, nature is prolific, robust, creative. It seems to work its way into every nook and cranny, right, here on planet Earth. So maybe on a world where these other easier mechanisms to create life aren't available, maybe with enough time you could invoke some weird, maybe silicate-based chemistry, or use liquid hydrocarbons as a solvent instead of water. But there are a lot of reasons why that's more difficult. Silicates can't create the kind of complexity that carbon can create. Liquid hydrocarbons are liquid at very low temperatures, so you don't have energy. Everything is going to be sluggish. So yeah, we have to, it behooves us to try and think of signatures of life that don't depend on how complexity arises and how genetic information is coded. And maybe just this basic idea of life harnessing energy to do work, maybe that's the most basic idea at the crux of everything. So if we can think of agnostic ways of finding life, that would be better. Yeah.
What's the furthest distance away from Earth you could look at it and be sure there was life here?
Good question.
And how would you do that trick?
So as I said, we're looking for all the planets that are closest to the solar system. If I want to measure the reflected light off of the surface of a planet and see oxygen in the spectrum, these wiggles, I'm going to build a 12 to 16 meter telescope, and I'm going to put it into space, and I'm going to observe all the stars within roughly, let's say, 100 light years. So that's, you know, and that requires already like a 12 to 16 meter telescope. So that's about the limit of, I think, what we can do right now.
Honor of the last question, and then I'll give you all home.
So I'm in the electrical engineering program here at Cornell, so I'm interested more in the technology side. Where do you see the technological limitations of what we have now? Is it in the sensitivity of the cameras? Is it in the computational power? Where do we need to make improvements to potentially see life?
I think that the technological challenge that we're facing right now is how to suppress the starlight very accurately and really carve a dark hole so that we can see very close to the star. And that's an active area of development right now. But looking even beyond that, I think that putting interferometers into space is going to be the next frontier. So interferometers are multiple telescopes that fly in formation, and they each collect light and then they combine the light. And that gives you amazing resolving power. And in the future, such a network of telescopes in space could actually resolve the surface of one of these planets, not just collect light off of a fuzzy blue dot that's unresolved, but actually see the surface, be able to delineate oceans and forest and land. So I do think that that's the far-term future beyond what I've talked about. So that's a great area of technology development to get into now.
And I think with that, let's thank Natalie again. Thank you all for coming and joining us.
Do not go gently into that good night. Thank you for coming.